Hello everyone. It's very funny to chair a session without seeing anyone. A bit like giving a lecture without seeing people. Anyway, we start this afternoon session with James Maynard from Oxford, and he's actually in Oxford. And he will talk to us about half-isolated zeros and zero density estimates. I think we can start now, please.
Okay, great. So thanks a lot for the introduction, Olivier, and thanks a lot to the organisers for inviting me to speak here. I'm very happy to be talking about this at Ballyfest. And maybe before I start, I should just mention that everything I'm going to talk about today is joint work with Kyle Pratt, who's also here in Oxford. And I guess a slight health warning is that we're still in the process of just writing up all the details. So this is very slightly work in progress. And so correspondingly, there's a slight health warning with everything that I'm saying, although we're pretty confident that everything's correct. So I'd like to talk about half-isolated zeros and zero density estimates. But to set the scene, we can start off with the Riemann hypothesis that I'm sure everyone knows and loves, that all the zeros of the zeta function have real part equal to 1/2. And the reason we care about the Riemann hypothesis is that it has lots of nice consequences for the distribution of prime numbers. So two of my favorite consequences are the fact that you get almost Legendre's conjecture that there's a prime between any two consecutive squares, that if you're looking at primes in intervals of length slightly larger than the square root of x, then you get an asymptotic formula for the number of these primes automatically if you assume the Riemann hypothesis. And then there's also a result of Solberg, where you get an asymptotic for primes in almost all short intervals, provided your intervals are maybe a bit bigger than log of x all squared. So the Riemann hypothesis is just a statement about zeros of the zeta function, but at least the reason I care about it is that you have lots of nice consequences for the distribution of primes, and in particular the distribution of primes in short intervals. But unfortunately, the Riemann hypothesis seems hard to prove. But one nice thing is that if all you care about is the consequences for primes in short intervals, then actually you don't need something quite as strong as the Riemann hypothesis itself. So for lots of these arithmetic applications towards primes, certainly not all of them, it's often sufficient to show that most zeros lie close to the half line rather than all zeros. So one way of measuring this is to let n sigma t be the count of the number of zeros with real part at least sigma and imaginary part at most t. So we're just counting zeros in a box. We know all the zeros have real part less than or equal to 1. So we're given some number sigma and some number t, and n sigma t just counts the number of zeros in this box here. And it turns out that if you have good bounds on n of sigma t, then you're showing that there are few zeros of moderate height that lie close to, that lie far away from the half line. And this is actually sufficient for proven results about primes in short intervals. So this is all very well known, but if, as a black box, you gave me a bound of the form n of sigma t is bounded above by t to some constant a times 1 minus sigma, then for the asymptotic for primes in short intervals, I get this whenever y is bigger than x to the power 1 minus 1 over a. And the proof of this is very short, and it's maybe quite illustrative for some of the things I would like to say later on in this talk. So I thought I would give a 3-line sketch. You want to understand primes in short intervals, so it's sufficient to understand the von Mangold function in short intervals. And you can use the explicit formula to write this as a main term, which is what we'd expect, and then plus some fluctuation, which is determined by the zeros of the zeta function. And I may be suppressing some small error terms and things here, so I'm lying slightly, but essentially the number of primes, the count of primes in the short interval has our main term, and then some what we expect to be an error term coming from zeros of height at most x over y. And I can split this count up according to the size of the real part, and I can bound the number of zeros with real part approximately equal to sigma by n of sigma t. And so I can just trivially bound this sum over zeros in terms of n of sigma t. And if I just plug in the bound that I'm assuming, then I see that whenever y is bigger than x to the 1 minus 1 over a, then n of sigma x over y is a bit smaller than x to the power 1 minus sigma. And so this gives us an asymptotic formula for the number of primes in short intervals. And the best known zero density result is a result due to Huxley, at least of the best known zero density result when it's just of the form t to some constant times 1 minus sigma, which is maybe the most important form of zero density results. It's this result of Huxley that n of sigma t is bounded above by t to the power 2.4 times 1 minus sigma. And so an immediate consequence of Huxley's zero density bound using the previous lemma is that we get an asymptotic for primes in short intervals where the length of the interval is about x to the 7/12 or slightly bigger. And Huxley's result is almost 50 years old, but essentially there's been no improvement on this zero density bound. And for the question of short intervals where we get an asymptotic formula for the number of primes, Heath Brown has essentially been able to replace a plus epsilon. He's been able to remove the plus epsilon, but otherwise this is essentially still the best known result for primes in short intervals and hasn't seen any improvement for 50 years. Similarly, you automatically get good results about primes in almost all short intervals, and those are also essentially the best known results. However, we believe that you should be able to improve this bound on n of sigma t, and the density hypothesis is the claim that you should be able to improve Huxley's 2.4 to the constant 2. And this is somehow a very natural limitation of lots of the methods used to study questions to do with the density hypothesis. Of course, we expect that n of sigma t should be equal to 0 as soon as sigma is bigger than 1/2. But the density hypothesis maybe represents one of the most optimistic extensions of the sorts of results that we typically use to study primes in these problems. And the nice thing about the density hypothesis is that from the point of view of primes in short intervals, or primes in almost all short intervals, this is almost as good as the Riemann hypothesis itself. So for example, you get an asymptotic formula for the number of primes in short intervals whenever y is slightly bigger than the square root of x, just in the same sort of range as we got with the Riemann hypothesis. And again, just falling short of Legendre's conjecture. So for at least the point of view of primes in short intervals, the density hypothesis seems like a possible substitute for the Riemann hypothesis, but we might hope that the density hypothesis is quite a lot easier to prove. And we can prove results in this direction which give us the best partial results. So this is Huxley's result, but unfortunately, the density hypothesis still seems difficult right now. But let's imagine we wanted to try and improve upon Huxley's result on primes and short intervals. So if you go through the sketch proof of the lemma that I wrote, you'll see that the key thing is to understand and get a good bound for this sum over zeros. And it turns out that if you go through Huxley's work, combining it with the earlier work of Ingham, you actually get you can improve the constant 2.4 to something slightly smaller unless sigma's very close to 3/4. So this means that if you want to get an improvement on results about primes and short intervals, you really only have to worry about zeros of the zeta function, which have real part very close to 3/4. And if you can get some bound on this sum over zeros, which occurs, that's non-trivial, so some improved bound, then you would expect to get an improvement in the length of the short interval that you can handle and still get an asymptotic formula for. So a couple of comments about this sort of sum. Even if there were lots of zeros, you might expect that this sum should actually have quite a lot of cancellation within it. And so if there was lots of cancellation, you would quite easily get results about primes in short intervals without necessarily needing to improve on zero density results. However, you would need to understand something about the distribution of these putative zeros if you were to show that there was cancellation, because if it was the case that there was some value x0 and x to the I gamma, where gamma goes through the imaginary parts of the zeros on the 3/4 line, if x0 to the I gamma all pointed in the same direction, say they were very close to being real numbers, then you would have essentially no cancellation in this sum, and your only way of trying to prove anything would be to prove that there are a few different zeros on this 3/4 line, or close to the 3/4 line. So in particular, there's a very clear obstruction to making any progress, which would be the problem of there being lots of zeros on the 3/4 line in a particular arithmetic progression. So sets of zeros in arithmetic progressions on the 3/4 line would be a very strong way of obstructing progress on primes and short intervals and lots of other related results about primes. And this sort of obstruction actually appears in quite a few different places. For example, if you started having arithmetic progressions of low-lying zeros for certain Dirichlet-Yale functions, this would also cause various unexpected behavior and problems in questions about, say, Chebyshev's bias and things like that. But it's a common obstruction that you run into, that there could be these arithmetic progressions of zeros as you go up the imaginary line. So the main result that I'd like to talk about today is a new zero detecting mechanism for what we call half isolated zeros. And the key thing that I like about this is that it's rather different to the standard zero detecting mechanisms, and in particular, it's somewhat sensitive to the precise vertical distribution of zeros of the zeta function. So most zero detecting mechanisms essentially are sensitive to the horizontal distribution, but they say nothing at all about the vertical distribution. And so in particular, this is somewhat addressing the potential problem that I mentioned on the last slide about arithmetic progressions of zeros on certain vertical lines. And this work was at least partially inspired by some much earlier work. So there was an unpublished note of Heath Brown on isolated zeros of the zeta function. And this was also picked up on and extended in a paper of Balasubramanian and Ramachandra. So it's very nice to be able to speak about something that was inspired by Balasubramanian's work in this conference. So before I get into precisely what this new zero detector mechanism is and what I mean by half isolated zeros, which is maybe slightly technical, even though I view that as the kind of main idea, I'd like to state a couple of consequences of this new unconditional zero detecting mechanism, which works very well if there's a certain amount of rigidity in the distribution of the zeros of the zeta function. So, for example, imagine that the zeros of the zeta function lie on finitely many different vertical lines. Under this assumption, our zero detecting mechanism works very well, and we get improved zero density estimates. So we can improve this 50-year-old bound of Huxley and also a now maybe almost 80-year-old bound of Ingham to get a improved zero density estimate. And correspondingly, if you improve zero density estimates, you improve results about primes in short intervals. So you get a improved result on the length of intervals where you can count the number of primes. So I should mention that we should be able to do a little bit better than 13/24 for counting primes in short intervals, although that's part of the write-ups are still in progress, and we can certainly get 13/24, so maybe we'll leave it like that. And we're stating the assumption that the zeros lie on finitely many vertical lines, because I feel it's the cleanest way of presenting our results, but we can certainly have much weaker but more technical assumptions. And the main point of this is slightly less conditional results, but we hope that this might lead to a new unconditional approach about primes in short intervals, although there's certainly new ideas are required if you're going to, say, make this corollary unconditional. So maybe that's a good flavor of the sorts of results that we're getting and the sorts of consequences we get from this zero detecting mechanism. But maybe I'll try and say a little bit more about what it is that we're really doing and what I mean by these so-called half isolated zeros. So I'm going to call a zero of the zeta function half isolated if every nearby zero either lies to the left of this zero or it lies above the zero. So it's roughly saying that there's no zeros to the right, but that's maybe not such a strong assumption because you expect, and we also partially know, that as you go further to the right, the zeros become rarer. And we're also saying that somehow there's no zeros directly below this half isolated zero. So it's half isolated because it's isolated to the right and it's isolated below, but it's not necessarily isolated above. And it's these zeros that we develop a new way of counting, and we can count these zeros unconditionally. So the work of Heath Brown and Balasubramanian Ramachandra, so RB should be BR, they showed a somewhat similar result under the rather simpler assumption that all the zeros were just to the left. And if all the zeros were to the left, then somehow zeros to the left become trivial in this setup, and so the number of such isolated zeros satisfies a density hypothesis type bound. So given that context, the key improvement that we have is that we're extending isolated to half isolated, which becomes a lot more technical to deal with. And so then maybe our main theorem is that there exists a short Dirichlet polynomial which takes large values near half isolated zeros. So maybe I'm lying very slightly in this statement, but there exists a Dirichlet polynomial with coefficients of size 1, which is a very short Dirichlet polynomial. So if you're looking at half isolated zeros of height t, then this Dirichlet polynomial only has length t to the epsilon, and this Dirichlet polynomial takes a large value, so it's close to 1 in size, whenever it's evaluated at a half isolated zero. So you'd expect as soon as you're away from the, well, I guess you'd expect that normally a Dirichlet polynomial should be taking exceptionally small values. So these large values are very rare, and therefore this is really detecting an unusual event. And the reason that this half isolated zero detector then gives various nice consequences if you assume that the zeros lie on finitely many vertical lines is because we start to get some fairly good distributional information about the vertical distribution of zeros of the zeta function. So if the zeros do lie on finitely many vertical lines, then they have to form these clusters above a single half isolated zero. So you can either a zero is half isolated, or there is a nearby zero on the same vertical line which lies below it, and you can just keep on therefore passing down, and so the zeros come in these clumps all lining up above a single half isolated zero. So in this diagram, you're supposed to be thinking about there being 3 vertical lines, sigma 1, sigma 2, and sigma 3, and the red crosses are supposed to denote half isolated zeros where there's no nearby zero below them, and the black crosses are not half isolated zeros, but they must all be occurring in some cluster above a half isolated zero.
James, does this say anything about what happens on the critical line?
No, not really. This is really only talking about things that happen away from the critical line. That on the critical line, suddenly it's not abnormal for such a Dirichlet polynomial to be taking large values, and so it doesn't really have any content. But as soon as you move away from the critical line, this is having non-trivial content.
Okay, thanks.
And so if you, since you have this nice clustering behavior, you suddenly have this fairly strong information about the vertical distribution of zeros away from the half line, and you can then work this into lots of traditional techniques for detecting zeros. In particular, it's combining this with the previous zero density type technology and making use of this clustering behavior that allows us to prove conditionally new zero density results if the zeros lie on finitely many vertical lines. And in particular, if the clusters are always small, as you might naively expect, if zeros are somewhat rare, then you suddenly get very strong bounds. So if you imagine that all the zeros occur in clusters of length big O to the epsilon, then this short zero detector would give not only the density hypothesis that n of sigma t is bounded above by t to the power 2 minus 2 sigma, and so in particular would give an asymptotic for primes and short intervals of length slightly bigger than the square root of x. We'd also get a essentially sharp bound for the fifth moment of the zeta function. So at the moment we know how to bound the first four moments, but we don't even know how to bound the 4 plus delta moment for any small delta, whereas we get the fifth moment if you assume that zeros lie on finitely many vertical lines, and then these clusters are all small. So quite a strong assumption, but strong and nice consequences if you make this strong assumption. So maybe before I move on, I'll just pause here to check that everyone is reasonably happy with what I'm claiming this main result is and how this corresponds. So the main result is unconditional about these half isolated zeros, but then if you combine it with the assumption of this zeros line on finitely many vertical lines, then this automatically gives some nice arithmetic consequences. Okay, seeing no questions or objections, I'll assume that everyone is happy with the main statement, and I'll move on to talk about some of the ideas that go into this argument. So maybe before I go into, maybe I'll start out with just a basic attack, which also incorporates the work of Heath Brown and Balasubramanian and Ramachandra. So you can just take your favorite smooth, non-negative function reported on the interval 1 up to 2, and let this have Mellin transform capital W. So little w is the smooth function, capital W is the Mellin transform. And I'm now going to consider the following sum. So it's just going to be lambda of n, little w of little n divided by capital N divided by n to the rho naught. So you should think of this, so this sum is supported on values of little n between capital N and 2 capital N. And so we should think of this as maybe some Dirichlet polynomial of length capital N evaluated at a half isolated zero rho naught. But for the moment, I'm not even going to assume that we can just think of rho naught as maybe some zero of the zeta function. So by Mellin inversion, I can just rewrite little w in terms of its Mellin transform capital W, and then I pull out the well-known Dirichlet series for the von Rangeldt function, and this n to the rho naught in the denominator just means that I'm shifting the argument slightly. I have this contour integral, and the obvious thing to do is to move the integral to the left. I pick up poles according to when the argument of zeta primed over zeta is equal to 1, or when the argument of zeta primed over zeta is equal to rho for some zero of the zeta function. And I get some leftover contour that's basically negligible, so I'm going to ignore it. So essentially, I can approximate this contour integral as the sum over all the residues. But since I've assumed that my function little w is smooth and nice, this means the Mellin transform capital W has very rapid decay. And so it turns out that essentially all the terms coming from these residues are completely negligible unless the argument of capital W is very small. And this means that up to some tiny error, this whole quantity basically reduces down to a sum over zeros, which are very close to our original point, rho 0. So if rho 0 itself is a genuine zero of the zeta function, then that appears in this sum, because certainly rho 0 minus rho 0 is less than log t squared, and that contributes a quantity which is of size about 1. So if there were no other zeros at all which appeared in this sum, then this would mean that we would have shown that this Dirichlet polynomial, which is quite short on the left-hand side, takes a large value at rho 0, because rho 0 would basically be the only term, and the whole thing would be of size 1. Similarly, if maybe rho 0 isn't the only zero, but all the other nearby zeros that occur in this sum have small real parts, then n to the rho minus rho 0 will be n to some negative power, and so all the contribution from each of these other zeros is also going to be small. So if all the zeros have real part less than the real part of rho 0 minus epsilon, so they all lie to the left of rho 0, then essentially they contribute a negligible amount, and so again the contribution from rho 0 dominates. And this is basically the argument of Heath Brown and Balasubramanian Ramachandra, that if we have an isolated zero rho 0, then the contribution from rho 0 dominates the right-hand side, and this means that there's a large value of this short Dirichlet polynomial. And this is how they're able to show that isolated zeros have short zero detectors. Unfortunately, this whole argument completely breaks down if you have maybe many zeros close to rho 0, which don't necessarily lie to the left of rho 0. So we would like to, a natural thing to try and do is to try and understand this argument and try and refine it to say also include these, to also include zeros that aren't isolated, and certainly to include half isolated zeros. So a natural question then is it always the case that when you have a zero, when you're evaluating at a zero rho 0, the right-hand side is large? It might be the case that even if you had lots of zeros nearby, the contribution from rho 0 always dominates in the way that it dominates when you have an isolated zero. So it's not too difficult to see that basically regardless of what configuration of zeros you had, if there's several zeros with similar real parts, then there are values of n and there are choices of capital N and your smooth function W, which means that certainly the sum can sometimes be very small. So maybe the next question would be, well, okay, there may be some bad choices of little w and capital N, but is it possible for this sum over zeros to really be uniformly small for all choices of capital N under consideration and all possible choices of smooth functions? It feels like we have a huge amount of flexibility to choose these, and provided we can find a good N and a good choice of little w for every 0 rho 0, then we should be able to construct something that at least looks like a short zero detector from that. But unfortunately, it can be the case that this sum is uniformly small if the devil is allowed to place where the zeros close to rho 0 are. And again, it turns out that it's our familiar enemy of the zeros lying locally in a vertical arithmetic progression. So if the zeros nearby to row 0 lie on a vertical arithmetic progression with common difference some constant divided by log t when we're working at height t, then for every choice of small n and every choice of smooth function w, this sum is actually tiny. And this means that if you were just in the middle of a vertical arithmetic progression of this type, somehow this approach of trying to find a short zero detector feels like it's doomed to fail. And we don't see any way around this at all. This common obstruction of arithmetic progressions on vertical lines seems to completely kill this approach. However, this very much relies on the fact that you're in the middle of a very smooth local distribution. And if there's somehow a discontinuity in the local distribution of zeros, such as the case with half isolated zeros, where zeros lie above, but they don't lie below, even if they lie in an arithmetic progression above, this whole argument, this whole obstruction goes away. And whenever there's some sort of disruption to a very regular local distribution, then I at least am not aware of any obstruction of this type. So it's only things that look like arithmetic progressions or unions of arithmetic progressions that I'm aware of that really cause this obstruction, that for every choice of capital N and every choice of smooth function, this sum over nearby zeros is very small. So you might therefore hope that you could prove something to say, if the zeros don't look like they lie close to some union of arithmetic progressions, or when, at least when you're looking close to row 0, then there is some good choice of capital N and some good choice of smooth function, which would allow you to create a short zero detecting polynomial. And we are able to do this, at least in the special case of half isolated zeros, where nearby zeros don't differ too much in their real parts, and they all lie vertically above the zero that we're interested in, row 0. And the key to this, which is maybe of independent interest, is a refined sort of Turan power sum type estimate. So maybe the simplest formulation is, if you pick your favorite R real numbers, then if you give me any superdyadic interval, then I can find some argument capital N for which this sum, which is modeling the sum that we had before, is not too small. So it's lower bounded by some polynomial quantity in the number of reals that we have. So you could apply standard estimates coming from Turan power sums, and that would show that there's some value of n in such an interval where the lower bound is instead exponentially small. So we get this sort of exponential improvement from an exponential lower bound to just a polynomial lower bound. And the fact that we can get this polynomial lower bound is absolutely vital for our method. So maybe a few remarks. Traditionally in Turan power sums, you look at integer powers of some fixed complex numbers. So you may be thinking about evaluating this sum S at powers of E, so maybe e to the L for integers L. but then the lemma would be false if you restricted to just a discrete set like this. So it's actually very important for our method that we allow completely arbitrary real numbers n within the superdyadic interval, and we're not restricting to some sort of well-separated set of reals. Because you can have counterexamples to the main statement then. Similarly, it's absolutely vital for our method that you have some positivity in the coefficients. So actually, it's important for us to have a rather weaker statement than just all the coefficients are +1. And we do allow for some negativity, but if you're allowing for arbitrary ± 1 coefficients, then you could choose theta j such that this sum Sn was just the expansion of 1 minus n to the power I divided by 2 log m to the power k. And the point here is that whenever n is between m and m squared, this quantity is going to be exponentially small. And this will show that you couldn't possibly have a polynomial lower bound. So it's very important, therefore, that we don't allow arbitrary ± 1 coefficients. And so we have some sort of positivity in our setup. I guess, as we mentioned beforehand, it's also very important that we have some sort of discontinuity in our coefficients, because we saw that if you're allowing smooth coefficients that can decay, then this sum can be uniformly small. And again, it can be almost exponentially small. So it's very important that there's this discontinuity, that we're summing discrete points, and the weights are either, at least in this context, 0 or 1, rather than having smooth weights. And the final point is that there are some choices of theta j when S of n can be polynomially small for all choices of capital N. And so up to the constant 100 here that we haven't tried to optimize, this is essentially best possible in this setup. So this is a very simplified setup. It's very much in the Jan power sum type setting, but it turns out that this sort of estimate is the key to allowing us to detect half-isolated zeros. So maybe I'll go through relatively quickly, but just the idea behind this power sum lemma is that since S of n is essentially an analytic function in n, we can understand Sn in terms of complex values of n. So just the basic principle that if you want to understand an analytic function, you can understand it on a wider complex domain and give lots of information about values within the complex domain. So we consider this related complex analytic function f of z, where I'm basically writing n as e to the power z. And clearly, at least in this setup, I can assume that θ1 is the smallest of the real numbers and that θ1 is equal to 0, because that doesn't change the modulus of the sum at all. And then if I evaluate this at purely imaginary arguments, because all the coefficients are 1, all of these terms become real then, and just the first term from θ1 gives me a constant 1. And so I know that at any purely imaginary argument, this sum always takes fairly large values. In particular, it's always lower bounded by 1. But on the other hand, I know that since f is analytic, the logarithm of the absolute value is subharmonic. So just to remind everyone, that means its value at a given complex number is upper bounded by the average of its value on a circle around that complex number. And so applying this to this complex number f of I log m, we see that we can apply this with bigger and bigger and bigger regions. So I can think about applying subharmonicity to ever-growing boxes, which are increasing to the upper half plane. And provided the function has sub-exponential growth, I can then bound the value at some complex point by a integral along the real line. So I can upper bound this large value by its values along the real line. And then just by using the trivial bounds that we've already seen, it follows straight away from this subharmonic inequality that f can't be very small on a whole dyadic interval, which corresponds to the original result. So it should be mentioned that when we came up with the proof of this, we were quite pleased with this, but we were trying to find if something had been done in the literature beforehand, because it sort of felt vaguely reminiscent of some of the arguments that occur with Hardy spaces and things like this. We weren't really able to find anything apart from, we contacted Jean Bourgain about it, and Jean Bourgain gave a independent proof of the same result, basically using the same ideas. And we also found that there was a Math Overflow post by Will Sarwin, who also comes up with essentially the same, fundamentally the same argument. But anyway, how does this relate to half-isolated zeros? So if you recall, we'd like to show that this local sum of zeros near a given zero, rho 0, is large to show that there's a short zero detecting polynomial. So zeros to the left trivially contribute some tiny amount in the same way that they trivially contributed a negligible amount when in the Heath-Brown or Balasi-Brahmanian-Ramachandra results. If the zeros, say, perfectly lined up on a vertical line, then this starts to look exactly like the situation that we had before, where theta j is just given by the difference in the imaginary parts, gamma j minus gamma 0. And okay, we have this slight extra complication from the smooth weight w, but we can say choose w so that it's non-negative on the imaginary axis, and we still have this discontinuity because we know that all the zeros lie above rho 0 whenever rho 0 is half isolated. And then you can adapt that Durand power sum type lemma to also handle this slightly more general situation, and that shows that there must be some value of n between, say, t to the epsilon and t to the 2 epsilon, which gives a large value, and so therefore proves the existence of a short zero detector for half isolated zeros. And so the key point is that it being half isolated and all the nearby zeros kind of crucially lying above the 0 causes this discontinuity that's necessary in our Durand power sum type lemma. So as soon as you have short zero detectors, there's lots of techniques that you can start to use. So the mean value theorem for Dirichlet polynomials becomes very powerful, and it automatically proves a density hypothesis type bound for half isolated zeros. So an immediate consequence of this is that the number of these half isolated zeros in a box with imaginary part at most t and real part at least sigma is of size at most t to the 2 minus 2 sigma. And moreover, if you assume that the zeros lie on finitely many vertical lines, then we can really start to use this vertical structure that we now know that the zeros must have, that there must be some small number of half isolated zeros, and then these dense clusters of zeros lying directly above the half isolated zeros. You trivially get a bound that if you're looking at clusters of length h, the number of total zeros is, well, the number of half isolated zeros times the number of zeros in a cluster. So it's bounded by h times t to the 2 minus 2 sigma. So you can refine this slightly, but this shows that you get a good bound for the number of zeros on the line with real part equal to sigma whenever you are looking at h being small, and so small clusters. And so the question then is, can I also get a good bound if I have much longer clusters when h is quite big? And so I would have these like very long, dense clusters of zeros, maybe on the 3/4 line. And this lemma is maybe a proof of concept that you can do better. And this is just exploiting the new clustering information with more standard zero detecting techniques. So again, in the interest of time, maybe I'll be slightly short, but the standard zero detecting techniques say that there is some Dirichlet polynomial of length m, which takes large values at any given zero. So this is different to what we had before, because these Dirichlet polynomials are not necessarily short Dirichlet polynomials. They could now be quite long Dirichlet polynomials. But if we're thinking of m taking a value of size m to the sigma whenever it's evaluated at a point with imaginary argument very close to the zero, then we can exploit clustering by saying, if I look at this integral of m to the power 4 evaluated at it times m to the power 2 evaluated at it plus ih, and integrate between t and 2t, and little h going between minus h and capital H, then whenever we're close to a zero, whenever it is close to the imaginary part of a zero, m of it is taking the value m to the sigma. But we also know that whenever we have a zero at it, if it's part of a cluster of length capital H, then all of these shifts, m of it plus ih, are also taking large values. And so the number of zeros that occur in clusters of length h provides a lower bound for this sum, and we see that it's of size r times h times n to the 6 sigma, since there's 6 copies of m, which all take in values of size m to the sigma, and where there's h different zeros in each cluster that are picked up by this h integration. But on the other hand, we can sort of fairly straightforwardly estimate this sum, and it turns out that you can bound it just by some Diophantine counting problem, and so you can get a fairly sharp bound for this using variance of the mean value theorem. And this simple bound here then gives an upper bound for r, which becomes very strong and much stronger than more traditional zero detecting mechanisms whenever capital H is large. So we're exploiting this clustering effect to get improved zero density estimates in this case. So if you combine this simple clustering bound with more complicated variants, but in the same sort of spirit, this gives our new improved zero density estimate when the zeros lie on finitely many vertical lines. And one interesting thing is the worst case scenario now is no longer when sigma is close to 3/4, it's when sigma is close to 2/3. Okay, I'm basically out of time, but as I mentioned at the beginning, our hope is that this is a new way of attacking questions about primes and short intervals that might lead to new unconditional zero density estimates. But there's one enemy scenario that we really don't know how to rule out. And so if you want to make progress on primes and short intervals using this line of attack, we need to rule out what we call bows of zeros, which cause problems. And we can think of this as the imaginary parts of zeros increase as if they're in an arithmetic progression, but the real parts smoothly increase from 1/2 up to whatever bad value of sigma that we're thinking of, and then smoothly decay back down to 1/2. And this is difficult for both of the two techniques that we're using, because if you look very locally, then the real parts hardly change at all. And so the zeros always look as if they're in the middle of an arithmetic progression. And so there's no discontinuity there. But then globally, because the real point, because these zeros are somehow connected to zeros on the half line, we can't use the clustering techniques that we're able to exploit in other situations. And this means that we don't have more global ways of exploiting these situations. And so somehow it doesn't work on either the local side or the global side. And so both of the two techniques that we're using to get these improvements fail to work in this situation. But morally, I feel that if you can handle this, then you're maybe well on the way to getting improved results about primes in short intervals and zero density estimates. So maybe I'll stop there. Thanks a lot for everyone for listening, and congratulations to Bala Subramanian and happy birthday.
So thank you, James. I don't know whether people can unmute to clap. So clapping is difficult at distance. If anyone has questions, well, I have lots of questions for this beautiful talk. A very simple one about this power sum like estimate. You have a lower bound which is 1 upon r to the 100. Well, and you have an example of 1 upon r. Do you have any idea of what should be the answer?
No is the short answer. That yeah, so I think the example does a little bit better than 1 upon r, but somehow the example doesn't feel terribly natural. So I would expect that the example is not the worst case scenario. Similarly, our method will give something a bit better than 100, although we haven't really optimized it. There's clearly still quite a large gap between the constants. The constants don't matter at all for our applications, but I would expect that neither the upper bound nor the lower bound are correct, and I really don't know where it would lie in the middle.
Okay. I have another question. You talk about a finite number of lines, but there should be some uniform. I mean, you should be able to link this number of lines with the height. What kind of link do you have?
Yeah. So if the zeros between t and so I guess the key thing is some sort of separation in the real parts. So if the zeros may be between t and t plus t to the 1/2, if the real parts, the projections of the real parts are either very close to one another or separated by maybe log t squared over log t, then the argument would work. So we could deal with log t divided by log t squared different vertical lines when you're looking between maybe t and t plus t to the 1/2 or something. So, I mean, that's really quite a lot of different vertical lines, I guess.
Yes. That's extremely sharp. I don't know whether someone has other questions.
Yeah, I have a quick question if I may ask.
Please.
Yeah, so my question is related to what Professor Rudnick was asking. So how close to the critical line we can go?
So again, this is okay. So in principle, as soon as you're a distance sort of log t squared divided by log t or something like that, so you'd expect if you're going a distance just a constant divided by log t, then you've basically not moved off the critical line and you're fundamentally still on the critical line. And we just need to go a little bit further than that for these results to start becoming non-trivial. So it's starting to say non-trivial things, maybe when you're log t squared divided by log t away from the critical line. That's the sort of thing that I would guess. Whether these results are doing better in that sort of regime than the much earlier zero density estimates, I'm not sure. So I don't know if these would really be competitive in that regime because there's certainly some losses in our argument. But this is saying something non-trivial, even very close to the half line, is my feeling, although I'd need to check a few of the details.
Yeah, thanks a lot. Thank you.
So let us thank James again, and if we can